Hello, welcome back to Control Systems lectures. In the last lecture, we showed how to design control systems to meet both stability and steady-state error. However, I stated that meeting these requirements does not imply that the desired transient characteristics are fulfilled. In this lecture, we will introduce the root locus method, which will eventually enable us to design a second and higher order control systems to meet all three design specifications, which are the transient characteristic, stability, and the steady-state error. Therefore, by the end of this lecture, you will be able to do the following. 1. Define a root locus. 2. Sketch the root locus of control systems manually and using Matlab and be able to interpret the results. 3. Evaluate the root locus for determining the poles of a closed-loop system. 4. Use the root locus to determine the system stability and transient behavior as a system parameter is varied for second order and higher order systems. The root locus is a graphical technique that gives us a qualitative description of a control system's performance. It is also a quantitative tool that gives more information than the previous methods we have discussed. So far, the gain and other system parameters have been used to design systems to yield desired transient response for first and second order systems. The root locus provides us with more capabilities to design for first, second, and higher order systems. Before we present the root locus, let us review two important concepts that we need for the discussion ahead. These are the control system problem, and second, complex numbers and their representation as vectors. Let us start with the main issues of control systems. Using the feedback control system in this figure and expressing our g of s as n subscript g of s over d subscript g of s and h of s equals to n subscript h of s and over d subscript h of s, where n and d are factored polynomials of the numerator and denominator. Therefore, our open loop transfer function will be given by k n subscript g n subscript h over d subscript g d subscript h, where k is the gain and n subscript g n subscript h are the numerators of the g and h respectively, and d subscript g d subscript h are the denominators. It is obvious that the poles can be easily found, as these will be the poles of the feed-forward and the feedback elements. Secondly, changes in k will not affect the open loop poles. On the other hand, the closed loop transfer function is given by t of s, which is equals to k n subscript g d subscript h over d subscript g d subscript h plus k n subscript g n subscript h. It is clear that we cannot determine the poles of t of s unless we factor the denominator. Let me illustrate this. Consider a system whose g of s is given as s plus 1 over s plus 2, and h of s is given as s plus 3 over s plus 4. The open loop transfer function will be given as g of s h of s, which is k s plus 1 s plus 3 over s plus 2 s plus 4. We can see that the poles are easily known to be 0, minus 2, and minus 4. On the other hand, the closed loop transfer function will be given as k s plus 1 s plus 4 over s cubed plus 6 plus ks squared plus 8 plus 4ks plus 3k. It is immediately obvious that the poles are not easily known, and secondly, the t of s will change with change in k. Since the system's transient response and stability depends on the poles of t of s, we can only know the system's performance if we are able to factor the denominator for specific values of k. This is where the root locus strength lies. The root locus is able to give us a clear picture of the poles of T of S as K varies. The second concept required for the understanding of the root locus method is the complex numbers and their representation as vectors. Any complex number, sigma plus j omega, can be graphically represented as a vector as shown in this Cartesian coordinate form in this figure. The complex number can also be described in polar form with the magnitude m and angular theta. If a complex number is substituted into a complex function f of s, another complex number will result. For example, if a complex function is given as f of s is equals to s plus a, substituting for the complex number s equals to sigma plus j omega yields f of s to be equals to sigma plus a plus j omega, which is another complex number. This number is shown in this figure. Note that f of s has a 0 at minus a. If we translate the vector a units to the left as shown in this figure, we have an alternative representation of the complex number that originates at the 0 of f of s and terminates on the point s equals to sigma plus j omega. We can therefore conclude that s plus a is a complex number and can be represented by a vector drawn from the 0 of the function to the point s. For example, the complex number s plus 7 as s tends to 5 plus j2 is a complex number drawn from the minus 7 to the point s, which is 5 plus j2 as shown in this figure. We will now apply this concept to a complicated function. Assume a function given by equation 8.1 where the symbol capital Pi means the product. M is equals to the number of zeros and n is the number of poles. Note that each complex factor s plus z and s plus p can be represented as a vector. The magnitude m of f of s at any point say s is given by the equation 8.2 where the length of a 0 s plus z with the bars in between meaning the length is the magnitude of the vector drawn from the 0 of f of s at minus z subscript I to the point s. Similarly, the length of a pole s plus p subscript j is the magnitude of the vector drawn from the pole of f of s at minus p subscript j to the point s. Then the angle theta of f of s at any point s is given by equation 8.3, where an angle subtended by a 0 is measured from the positive extension of the real axis of a vector drawn from the 0 of f of s at minus z subscript I to the point s. Similarly, an angle subtended by a pole is measured from the positive extension of the real axis of a vector drawn from the pole of f of s at minus p subscript j to the point s. We will now use an example to demonstrate this concept. Given the function f of s is equals to s plus 1 over s plus 2, find the function f of s at the point s equals to minus 3 plus j4. To solve this problem, we need to find both the magnitude and angle of this function from the complex number. This problem is graphically represented in this figure. We draw each vector to terminate on the selected point s equals to minus 3 plus j4. The vector originating at the 0 at minus 1 has a magnitude of square root 20 and an angle of 116.6 degrees. And the vector originating at the pole at the origin is 5 magnitude and angle 126.9 degrees. The vector originating at the pole minus 2 is square root 17 magnitude and an angle of 104 degrees. Substituting these into equation 8.2 and 8.3 will yield our result as the magnitude being 0.217 and the angle minus 114.3 degrees. Please complete the skill assessment exercise 8.1, which is in page 391 of your textbook. Thank you for listening, and please prepare your questions so that we can discuss them during the next class.